1110 delete nodes and return the forest. So we are given a binary tree and we are given to delete like 3 and 5 the values that we have to delete from the tree. Thing to note that these are not the tree nodes, they are actually the values. So first we have to identify the nodes, then we have to delete it. Okay, and then what if, assume in this picture example 1, if we delete 3 and 5, 3 will be removed. So this branch, right, it won't be here anymore, and this all hold together. So 3 to 6 that is right now connected will be disconnected because 3 is not there anymore. And at the same time we have to delete 5, the 5 will also be removed. So what we'll have? We'll have a tree where 1 is connected to 2, 2 is connected to 4. So 1, 2, 4. So this one what we have returned. And similarly we have to return these nodes also because they are not disjoint. They are not connected to each other. But at the same time we have to return it. So before we head into this question, we have to understand the underlying concept. If we wish to delete, let's say there are multiple nodes to be deleted, but assume that we only have to delete a single node. Let's take the example of 3. If we just have to delete 3, right? If we just have to delete 3, what we'll do? If 3 is not there, so 3, we have to break 3 links, right? From its parent, it has to be discarded, and 3 to its child, if it has any. Like in the 5 case, it doesn't have any child, so no point, right? And then 2 to 5, this has to go away. So in order to break the parent link, we need to know, right? We need to know whenever we encounter any tree node that has to be deleted, we have to know its parent because we have to delete its parent now. Parent to child link we have to break. And if we are on the tree node itself which has to be deleted, then we can simply check its children and then break the link and we'll add them to the result. But at the same time we have to be very careful while adding. We have to see if this one also needs to be deleted. Let's say we had to delete 3, 5 and 7. So we deleted 3. So we will try to add 6 and 7 to our result. But at the same time we have to see if 7 has to be deleted or not, and 6 has to be deleted or not. If they are to be deleted, then we'll not add them to the map, right? I mean not to the result. So let's see how we are going to solve it. So we'll just create let's first to check if it's which has to be deleted, let's store them into the set so we can easily search on it. So to delete, these many we have to delete. I'll create a hash set. Alright. Now what we'll do, we'll add all the values which has to be deleted to the set. Okay. To delete dot add. So these values we have to delete. Alright. Now our job is, okay, we have to results, add a list, right? List, we have to result the results. So let's take it. Result, which store our final answer. And then what else? Then I think it should be fine, right? Let's see. So we'll call a delete function, return, or maybe like delete nodes. We'll pass the root. We'll pass which has to be deleted. We'll pass the result where we'll store our result and the parent. But right now, since we calling from the root, it will be null. And if we try to make the function now, so it has to be static, it will do nothing, and what else? Nothing. So we'll just define it. So tree node, our starting node is root, comma 2, okay, it's a set, right? Which one to be deleted? Then finally our result. And tree node parent. Alright. So now what we'll do, we have to see if this certain node, right, we are at the root node, and if we have to delete it or not, right? So how, when we are going to end this iteration, if let's say root is equals to null, so we'll just return the time it will end. Okay. So now see, if set dot contains, let's say, root dot val, right? So this has to be deleted. If it has to be deleted, so what we'll do, we'll check if parent is null. So it's a root node, right? It's a root node. So if we delete this root node, right? If we delete this root node, we just have to add its child to our result. If not, we will see if the parent is null. Else what we'll do, if the parent is null, if not, so suppose we stumbled upon 3, right? So first we have to break this link, and these 2 needs to be added only and only if they are not in this set to be deleted, right? So first to savior this link, so if, so parent, obviously we are checking parent is null, so it goes here itself, but somehow parent is not null, then it has come here. So I'm assuming, so we need to know whether the parent, from the parent to child, whether we came from the left or from the right. So if parent dot left is not equals to null, so we have to break this link, parent dot left, assume 2 is our node, this has to be deleted. Parent dot left is not equals to null, we have to make this one null now. Parent dot left will be null, or else it was on the right. So parent dot right will be null. So this part is done. Now we have to add them to delete, right, to the result, and only if we can add if that's not present in the set. So if set contains root, right, root dot val, if it doesn't contain, right, then we can surely add them root dot left. So we'll add to our result dot add dot root dot left, and if same thing, if set dot right those childs, it's not there, so we'll add them also. So we have added these, all right, and this connections, right, this has to go away. So what we did, we found our value, right, this is equals to value. So we'll try to break this link. So if the parent is null, we'll do something, but if the parent is not null, so we break the parent link. So this will break the parent link. Now the parent link is gone, we have to break these also, and we have to add the children to the result only and only if it's not to be deleted. So we have added them to the result if they are not to be deleted. All right. And moreover, we have to say check if they cannot be null also. Root right left shouldn't be null, because with no point of adding null to our result. And similarly, root dot right should also not be null. Then only we'll add it. All right. So this is for the delete, but at first we have to identify, right, which one to delete, because right now okay, it has severed, and assume it's a parent is null. So parent can be null only in the case of root. All right. So what we'll do, we'll simply try to add these its children only and only if they are not null, and the same thing. So I'll just copy this part. Parent is null, this will happen. Okay. So anyway, this is a common section if it contains, so we can simply write it outside here also. And we'll just delete from here. So if parent is not null, so we have a parent, break the parent link. Parent link and child link. We are adding the child to the results. All right. And if it doesn't contain, so we have to move to the right and left. So again, we'll call the delete node itself. If, okay. We'll call it if root dot left isn't equals to null. So we'll call for the left. And now parent will become root. And similarly, we'll do it for the right. Parent will root. It will be root only. And this will become right. Alright, and so once it's returned to the very end, it will return null. We're breaking the link. Is there anything left? Now, let's see what do we get. Return result and try to run it. Okay, single. Cannot find the. Okay, it's actually not said, it's to delete. Okay, so to delete contains to delete. All right. And now, okay, we got the wrong answer. Why? 1, 2, 3, 4, 5, 6, this was given. We got only 6, 7. And all right, 6, 7. So I'm assuming if we see the test case, what just happened? 6 and 7. 3 got deleted. What about 2? Did 2 even got deleted? It started iterating. If it will check if root, so it won't go into this one contains right. It will go to the left and go to the right. So first to the left, yeah, it will be equal, right? So once it's equal, root dot val 2 is equal. No, 2 is not actually equal. Then it went to 4, then eventually to 5. So 5, yeah, 5 is actually equal. So it will check if parent is not null. Okay, it will come to this section. Parent is not null, so parent dot left if not null. No, actually it has to compare with the root, right? Parent dot root. If parent dot left is equals to root, then we make it null, else to right. That's how we know the link, right? Okay, 1 is not returning. Why is that? Because why is that? Okay, we deleted 5, got shivered, and when deleted, we added these 2 only. But we have never added the 1. We have never added 1 to the result. So for that, what we could do, if this is not to be deleted, right? So we'll add it, right? We'll add to the result. The result dot add, no, but not every time. Only if it's the root, right? So if only else if parent is equals to null, then we'll add the root. Okay. If parent is null, then we have to add the first section, and let's submit it. And it's done. Yeah, so how this is how we'll make it. So it's pretty straightforward. If you just see what we had to do, we stored everything to be deleted in a set. so that we can easily search on it. This is our result, and we called our function which is going to actually delete it. When we entered in the function, this is basic condition. If it's null, we'll just end this. And if somehow the current node that we are standing at, right, if it has to be deleted, then we have to do three things. First, we have to break the link between the parent. So how would we know if it has a parent or not? So we'll check if the parent is null or not null. If it's null, then it's fine. There's no need to break because then it's a root node. So if it's not null, so we have to break it. So we need to know the link between the parent. So there could be two possibilities, right? If the from the parent to the child, it must have been a left one or the right one. So if the parent dot left is equals to root, so this was our link, right? This actually shows the link parent dot left is equals to root. So we'll make it null. So if not, then obviously we have came from the right side, from the parent to child. So we'll make that link null. So the parent link got severed. Now what we have to do, we have to check. We have to break the child links, right? So in short, we have to add the results, the childs to the result, only and only if they are not to be deleted. So we'll check if it's not null and they are not to be deleted, only and only then we'll add them to results. So 6 and 7 we have added to the results. If somehow we have to delete 7, so we won't add the 7. And other condition would be if it's the root node itself, right? If the parent is null and it has not to be deleted, in that scenario, this has to go to my answer. So what we'll do if the parent is null, so it's a root node, so and it is not to be deleted, so we'll just add it. And recursively we'll call for the left node and the right node, and this will take care of it, and it's done.